So with our carbonyls, again noted in the middle, aldehydes or ketones is our primary focus right now. We aren't concerned about esters, acids, acyl chlorides, amides, any of those. Okay, we're really just focused on that carbonyl or a nitrogen, so imine. Okay, so 1 and 2 need to be carbons or hydrogens at this stage. One thing we can do is always look to the resonance structure, and the resonance structure will call attention to the chemistry of that compound, where you now have a negative oxygen and that positive carbon. Okay? The negative oxygen can't really act as a nucleophile because its electrons are preoccupied with the pi bond, or stabilizing that carbocation. Okay? It could potentially act as an acid, particularly if we put in a strong acid. The strong acid will now force those electrons to react. Okay? So when we look at the carbonyl structure, its primary reactivity is in that carbocation. We have a really good electrophile, which means everything that we talk about is now how do nucleophiles react with that electrophile. And so we looked at a bunch of reactions, the lithium borohydrides, the sodium borohydrides. We've got our Grignard, we've got our Wittig up there. Okay? And then we have Grignard type reagents. Okay? This would be an organolithium compound. And we also have the acetylide option possibly popping up every so often. Okay? The next part of this chapter, as we move into chapter 18, which is looking at weak nucleophiles, okay, or rather weaker nucleophiles, is what happens if I take that same carbonyl except put it near another functional group. And in particular, I'm going to put it near an alkene. Okay? Does that change the chemistry of pretty much everything? Okay? Well, so starting off with the carbonyl, would I expect the alkene to change a lot of the chemistry of the carbonyl? Okay? And why or why not? I would argue no, that the alkene shouldn't change too much the chemistry of the carbonyl. Why? The carbonyl is polar. We have a large difference in electronegativity. That large difference is going to trump the proximity of the other functional group. Okay? Because that other functional group isn't really contributing a polarity. Okay? Will the carbonyl affect the alkene? Well, how would we expect an alkene to react? A nonpolar pi bond. How do nonpolar pi bonds react? As nucleophiles or bases. They immediately donate electrons out. Okay? Does putting the carbonyl close to that nucleophilic source change anything about those electrons? Well, what does the carbonyl have a lot of? Kind of a horrible statement, so I'll just give you an answer on that one. Okay? Polarity. Okay? A large difference in charge there. So what is that alkene going to do immediately? It's going to immediately try to stabilize that large polarity difference, which means where do those electrons immediately shift to? Going towards the carbonyl. Well, if they now go into the structure, can those electrons act as a nucleophile anymore? No, because to act as a nucleophile, the electrons must leave the structure. We've now given the electrons an alternate place to go within the compound. We've nullified the nucleophilic ability of the alkene. Does that nullify all of its chemistry? Well, what happens if those electrons shift into the structure like that? What would we get as a resonance structure? We'd get a negative oxygen. And just like we had with the carbonyl, we wouldn't expect that negative oxygen to be a good nucleophile because, again, it's preoccupied with sharing most of its electron density into the structure. And then I interrupted you because I wanted to finish that statement. A positive carbon right at the end. And an internal pi bond. A pi bond immediately connected to an oxygen known as an enolate. Remember how I said enolates are important? We don't start with an enolate here, but the reactivity of that structure goes through an enolate intermediate. The important part of addressing this resonance is that we now find we have two electrophilic sites. We have the carbonyl carbon and we have the blue carbon in my drawing, which if you look at the slides you can see is blue. Okay? Both of those are electrophilic sites. So when I look at the alpha beta unsaturated ketone, alpha beta meaning there's my ketone. What's the first position? Alpha, the next position, beta. If I have an alpha beta unsaturated, what does unsaturated mean? I've removed hydrogens. In the process of removing hydrogens, what have I placed? A pi bond. Okay? So an alpha beta unsaturated carbonyl is really an alkene conjugated with a carbonyl. Okay? That conjugation brings in a new site of reactivity, and we get two places where we could do a nucleophilic attack. Okay? We have the large partial positive of our carbonyl, and then we have a slightly smaller positive of the alkene on that terminal carbon. Okay? Why is the red carbon more electrophilic than the blue carbon? It's closer to the electronegative element. It's closer to the oxygen. So the red carbon is a more positive structure than the blue carbon. So if I were to mix this structure with a nucleophile, where would I expect the nucleophile to go? I would immediately expect it to attack the nucleophilic or the carbonyl carbon, okay, our red carbon. And we would get the product shown mostly in chapter 17, where we have a direct nucleophilic addition. Okay. Mostly chapter 18 and sort of only mentioned there. Okay. And the tail end of chapter 17 says that the other carbon can react. Okay. What differentiates between those two? Well, in chapter 17, we're looking at what nucleophiles? The strongest, also known as the stupidly strong nucleophiles. In chapter 18, what have we moved to? Strong nucleophiles. Okay? Because they are slightly weaker, that provides enough time that we now favor a thermodynamic product.
Which one favors thermodynamic?
The weaker nucleophile.
The blue one.
Just like the weaker base. Okay, favored the thermodynamic product. So if we go back all the way back to our enolates, like 2 weeks ago where I screwed up that lecture, and then we fixed it on Monday, and then I didn't record it last Monday, all that fun stuff. Okay. The stupidly strong bases, okay, removed the kinetic spot. Okay. They removed the most accessible hydrogens. The stupidly strong nucleophiles are going to attack the most electrophilic position because they're trying to neutralize their charge as quick as possible. So they're going to seek out the fastest positive. Okay. The less strong nucleophiles now have a choice. Which positive do I want to go to? Okay. I'm not insanely reactive at this point, so I'm going to now decide which one to go to. That decision process is ultimately a way of saying we end up with the thermodynamic product. Where this becomes tricky is when we compare those structures to each other, deciding which one is kinetic or thermodynamic or even more or less stable becomes very, very challenging to determine. Okay? And we will look at that here in just a second.
So why, when you have a stupidly strong nucleophile, why doesn't it, because you have like acidic hydrogens, right, like on position 1, like why wouldn't it just take a hydrogen?
So position 1, we haven't identified anything out there, so I'm going to say that's a bad position to identify.
If it was a carbon.
Okay, so if it was a carbon and we put a hydrogen there, we do have the potential for that to be an acidic hydrogen. So now it's going to come down to our nucleophile. Is it best to act as a nucleophile or best to act as a base?
Hindrance in it, and, okay.
Yeah. And in this case, we're ultimately looking at stupidly strong nucleophiles, hydride, okay, and the Grignard nucleophiles. Well, the Grignard is so sterically hindered that it could act as a base, but it's preferentially going to react with the pi system because the pi system is more accessible. Okay. Hydrides. Well, wouldn't hydrides attack the acidic hydrogen? Okay. Well, again, it depends on the hydride. Sodium hydride only has that option. borohydride and aluminum hydride now have the aluminum and the boron to help stabilize it such that it interacts better with the pi system. Okay? So we have explanations-ish behind those, but ultimately those explanations came after we ran the experiment and we're coming up with an explanation behind it. Okay? Those explanations might make sense to you, they might not. What are you ultimately responsible for? Not quite a good enough answer for me. You're responsible for knowing what lithium aluminum hydride does. What is its primary reactivity? You're responsible for knowing what sodium borohydride does. What is its predominant reactivity? You can come up with an explanation and derive that effectively, but on an exam it may be faster to just have that content memorized. Okay, so really you need a blend of both. Okay? So let's take a closer look at our carbonyl. There's our resonance structure, and this is where we end up with the reference to 1,2 versus 1,4 conjugate additions. Okay? The numbering 1,2 versus 1,4. So let's take a look in the starting structure. Where is position 4? The fourth carbon. That makes sense because of nomenclature, right? What are you complaining about, Mo? There's not 4 carbons. So when we're talking about 1,4 and 1,2 additions, it has nothing to do with the nomenclature system. It's referencing the atoms that have potential reactivity. How many atoms that have potential reactivity in that structure? I count the oxygen as part of it. And so when we're looking at that 1,2 versus 1,4, this is 1, 2, 3, 4. So when I do a 1,2 addition, what's happening?
You're adding something on the oxygen.
I'm adding something to the oxygen and adding something to the carbon. Okay? That is our standard nucleophilic addition that we've seen before, say with our Grignard. The nucleophile comes in, attacks. There's our carbon. I should have just drawn that as a nuke. Oh well. Step 2, H+. Attacks. What's the result? What have I added to the structure? What are the new things I've added? Where did I add them? I add them at the 1 and 2 positions. So it's a 1,2 addition. Okay? In the case of the carbonyl, that's a rather straightforward argument because where's the reactivity? Only at position 1 and 2. So I don't refer to nucleophilic additions to just standard carbonyls as 1,2 additions. They are, but why? Okay, why reference it? That's the only place where chemistry is happening. What happens when I go through and change my carbonyl to now being an alpha-beta unsaturated ketone? Do I have more than 2 sites of reactivity? Yes. Okay. And now when we go through and run this reaction, the nucleophile could have attacked the other electrophilic site, causing that sequence. And what do I get as an answer? Whoops, and I left the pi bond off, sorry. Everybody see that? Okay. Just to throw an extra massive wrinkle in this, the 1,4 addition that is drawn there, you will never see that drawn as the product. What you see drawn as the product is this. Where did you do the addition in the case of the 1,4? So our bottom line is our 1,4. The top line is our 1,2. Everybody see where the 1,2 added? I'm going to take that as a yes. If we look at the 1,4 as we stepwise through it, right, there it makes sense. It's position 1 and position 4. And yet the product that we always see for the 1,4 addition is not the one that's red and blue, it's actually the purple one. That's the structure that's drawn as your final product. Where does it appear that you added things? Well, you've got the carbon for sure. Where was the other thing added? What was the other thing added?
Looks like hydrogen.
A hydrogen, which was added. It's the alkene, right? 1, 4. If I'm correct, 2 comes after 1, 3 comes after 2, and then 4 comes after that. So if I say the carbon attacked position 1, then I would need to go through 2, 3, 4 to see the fourth thing added. And yet, when I look at what's actually provided as the answer, where's the thing added? Appears to be added to the 2 position. Where's the disconnect? The chemistry in red is 100% perfect-ish, okay? Because I don't know that I can verify that. Yeah, that's fine. Okay. A step 2, H+, right? Chemistry in red is fine. Chemistry in blue is fine. Why the hell is the 1, 4 shown in purple and not the red one?
Are we in an acidic environment?
Not a bad idea, considering the environment that we're in. Doesn't matter.
So do you get the 1,4 product and then to topolizes to the more stable one? Is that
What functional group is this? It's an enol. What do enols do? Tautomerize to the ketone. Why do we never see the 1, 4 product? Because that product changes its structure, the orientation of those atoms, to put us to the purple product. The purple product is our more stable product. That's why we end up with that one. So this 1, 2 versus 1, 4 tends to confuse students because it always looks like a 1, 2 addition, just different 1, 2 additions. Okay? The 1, 4 is because we're forming an enol, the enol switches out to give us our final product. The chemistry is still a 1, 4. Kind of, sort of? Okay. The 1, 2 is sometimes referred as a direct addition, which was our most electrophilic site in our alpha-beta unsaturated ketone. The carbonyl carbon. It was the most positive, so a direct addition directly adds to the most positive position. That's why we call it a 1, 2. Because when we number out, if oxygen is 1, we're directly adding to position 1 and 2. We're directly addressing the largest charges in our structure. Okay? The 1, 4 is also referred to as a conjugate addition. Why a conjugate addition? Where's your nucleophile adding? To the carbon of an alkene that is conjugated with the carbonyl. That's why it's referenced as a conjugate addition. Kind of, sort of? Okay. So, the line between which one we get in which case comes down to the strength of the nucleophile. If it is stupidly strong, we get direct addition. This is why our hydrides add directly to the carbonyl. They don't add to the alkene. Grignards add to the carbonyl. Why would they add to the carbonyl? What is a Grignard? A negative carbon. I didn't hear what you said, but I heard negative carbon. Was it negative carbon?
No, I said it would be direct addition.
It is a direct addition. That's the definition of 1, 2. It's a negative carbon and negative carbons. Would we predict those to be stupidly strong or just strong? Stupidly strong because
Doesn't like to be negative.
carbon can't stabilize a negative charge. So we would expect our Grignards to do a 1, 2 addition. Right? So let's go ahead and take a look at this tail end of chapter 17, okay, with just our strong nucleophiles. We've got a new named reaction called Gilman. Okay. What changed is we went from our alpha-beta ketone to our product. What did we add to the structure? An R group. And what is an R group? A carbon. Okay. That carbon is attacking the electrophilic carbon of our ketone, or our alpha-beta ketone, right? Which means that R group is what charge? Negatively charged, right? It's attacking an electrophilic site. So that R group is negative. We have a negative carbon. What are negative carbons? Stupid strong or strong? Stupid strong. Where should the negative carbon attack? The carbonyl, did it? No. Why not? Okay. This is yet another reason why we can attach a name to this reaction. Everything about the reagent chemistry should suggest it attacks 1,2. It doesn't attack 1,2. Why does it not? Oh, somebody sat down and said this is why it doesn't do it, or came up with a theory for it. Because everybody assumed that it would do one thing, but it did the other. Whoever went through and explains that now gets to attach their name to it. Okay? So, why is the R in the Gilman reagent not a stupid strong nucleophile? Okay? Well, what made the R a stupid strong nucleophile in the Grignard? How is it charged? Magnesium carries a positive charge. So when I look at the bond between carbon and bromine, carbon being more electronegative than magnesium does what to those electrons? Takes them away. Meaning the carbon becomes very negative. What is the R group connected to in the Gilman reagent? If it's connected to the bromine, what charge is the R group? It's positive because bromine is more electronegative than carbon. What do we mix it with? Lithium. What does the lithium do? It's lithium solid. So what does the lithium reagent do in that first step?
Somehow makes R negative.
Okay, I'll accept that. Somehow it makes R negative. Just like with the Grignard, the lithium will insert itself into the bond, and we end up getting lithium bonded to the R group, which gets us our negative carbon. To balance this out, we also have to form lithium bromide. Okay, that's a more complex mechanism than it is for the magnesium. Okay, and we could, but then that begs the question, well, if I start with this, okay, or if I ask a question about lithium R, but then someone shows RBR lithium, would you know that it made that? Not necessarily. So I'm providing the context. Just like with the Wittig reagent. We could show 3 steps or we could do it in 1, depending at what stage we decide to drop you in. Okay?
As long as we know the R is negative, right?
As long as you know that the R becomes negative. Okay? Well, what is the difference in electronegativity between R or carbon and lithium? It's large, right? Is it larger than between carbon and magnesium or smaller? Okay. Smidge is probably appropriate because it's also nice and vague enough that we could say it's a smidge larger or a smidge lower. Okay. Why might we say it's a smidge larger? Lithium is one group to the left, which means its electronegativity should be smaller. Okay. Why might we say it's a smidge, the other smidge? It's one group higher, which means its electronegativity is a little bit higher. Pretty much either way we look at it, the difference in electronegativity between those two is large. Okay, between carbon and lithium, and the difference between carbon and magnesium. The magnesium and the lithium are not far enough away from each other to generate a difference in electronegativity with carbon that is significant, okay, or significantly different from each other. Which means the negative carbon produced with the lithium and the negative carbon produced with the magnesium are identical. So if I said the magnesium one was a stupid strong, what is the lithium? Stupid strong. Still didn't look at the reaction. That's not where it's attacking. Is there another step in this reaction? What is that other step? I think I see where you're getting cul-de-sac. This is Cu, copper, iodide. Okay, put the little serifs on there a little bit better. Okay. What is copper? A metal. Guess what copper does? It substitutes out the lithium. So at the end of step 2, what do I end up with? I end up with R times lithium.
Well, copper is usually a +2, so does that help even more like magnesium does? Because lithium is usually +1. The lithium starting out as a solid.
The copper does go through a redox reaction where it shifts to becoming a +2. It starts at a +1. It will eventually come down to a +2. And And we end up with the state where I have 2 R groups connected to 1 copper. So the copper does change its oxidative state. Okay? More advanced than you really need to know. Ultimately, what you need to know is that copper inserts, and instead of having lithium connected to the R group, we now have copper. Does that change the negative character of our R group? Yes. Does it change it significantly? And a good question would be, well, how? How did we get the negative character established in RLi versus RMg? What did we look at? Electronegativity. So what should we look at to determine the negative character between R and Cu? Electronegativity. Where is copper on the periodic table? Way over here, which means its electronegativity in comparison to magnesium and lithium is greater, which means what happens to the difference in electronegativity between copper and carbon? Becomes less, which then means the carbon is no longer as negative. How much not as negative? Sorry, I got no answer for you. Okay? Everywhere we move in OChem, there is always a line, okay, where things go from being strong to not strong. Okay? Where and how we establish that line is ultimately from experimental evidence. That line happens to fall right above the Gilman line, or Gilman reagents, meaning the Gilman reagents no longer a stupid strong nucleophile. They are a strong nucleophile, which means when I see that copper pop up, if I have an alpha beta unsaturated carbonyl, the R group will attack the alkene. Okay? I may not be happy that I have to memorize that line, but that's one thing to memorize as opposed to having to memorize all of it. So I would make the argument that everything on here is relatively simple based off of differences in electronegativities and predicting where things attack. The one thing that stands out in this spider diagram that is like, what the hell, is this lower right-hand corner. As a what the hell argument, that's where I'm going to memorize. The rest of it I can derive because it's following standard patterns of chemistry.
So you say that copper is more electronegative?
Copper is more electronegative than our lithium and magnesium. More electronegative, so pulling the electrons on the carbon more, which means the carbon becomes less negative because more electrons are coming away from it.
So it's still...
It is still a negative carbon. Yep. It is just less negative. Okay. Questions on that? So how did we get 2 of the R groups? Ultimately comes with the mechanistic detail of how copper inserts itself into that. Copper starts as a +1 here, and it becomes a +2 through a bunch of electron transfers. If you would like to know that mechanism, talk to me at the end of the semester, and I will help figure out a mechanism for you. Okay? I believe that if you actually look up a mechanism online, what they end up showing you is a kind of cyclic cycle on it, because it's not an easy, straightforward mechanism. We don't know exactly how the copper is transferring those electrons. Okay? You might say, well, that's silly. We've done this before. Did we show exactly how the electrons were being transferred with osmium? Or with manganese? Okay? No. The transition metals have weird chemistry because they have access to the d orbitals, and those d orbital electron systems make it more complicated to run a mechanism, because most of our mechanisms are based off of Lewis structure, which was originally designed after an octet. Why has copper become tricky when we consider an octet? Because it has the d orbitals, it can exceed the octet. Why is sulfur tricky? It has access to d orbitals because it's in the 3rd energy level. That's why it can exceed the octet. Same deal for phosphorus. Right? Lewis originally looked at those and went, that's complicated, I don't want to look at that yet, and built his theory off of the 2nd row and above. Right? Once he had a theory there, he tried to scaffold it out to the rest. And it has some parallels, but there's also some weaknesses. Okay? So, 1, 2, and 1, 4. How does this work for our kinetic and thermodynamic? Okay? Because that is ultimately what is happening here. So, we've got our starting carbonyl, we've got our nucleophile that can do a direct, oh, I forgot, this one bothers me. No, it bothers me because it's not color-coded right. No, we can't skip it. Okay? If the nucleophile attacks the carbonyl, okay, we would have the direct addition. Okay? This would be the beginnings of our 1,2 direct addition. If the nucleophile instead attacked the alkene, what happens? Okay. Well, now I've got the beginnings of the conjugate, okay, or the 1,4 addition. Which of those two structures would I expect to be more stable? Why would you expect the top one to be more stable? Oxygen has a negative. That's a phenomenal guess. But just like we saw with our enolates, what do we need to evaluate before we start immediately comparing structures? We have to consider our resonance contributors. In the top one, do I have a resonance contributor? Can those electrons come back down? No. There is nothing that I can do with those electrons. They're stuck there. Hence, you'll notice that the arrow shown to the next step is not a resonance arrow, it's a reaction arrow. If we look at the bottom one, could I move those electrons over here? What would be the problem if I moved them there? I would exceed the octet on that carbon, but I have a weak pi bond that I can then move. The result is I end up with the next structure. Is that a valid structure? Yes, because so, I now have a resonance contributor, and I now need to evaluate said resonance contributor. Yeah? Okay. Now I can make a comparison between my red product and my blue product. Which of my blue structures should I compare to the red one, left or right? Why the right? It's putting the negative charge in the same location. It's minimizing the difference between the structures. Okay? How would I tell a difference now between them? Which one's higher or lower in energy? The blue one is lower because if we look at the pi bond, it is a more substituted pi bond. Because it is a more substituted pi bond, it becomes more stable. Okay? We've only done one step. Okay? So we start with the exact same reactant. Okay? And we're now shifting to intermediates. Okay? Which one is intermediate 1? Blue or red? Why blue? It's the more stable. This is the pathway for our conjugate 1,4 addition. Okay? The red one, being less stable, is our pathway for our direct or 1,2. Okay? This is why I'm going to get irritated by color coding. Thermodynamic or kinetic? Which one? Red or blue?
As far as which one happens first?
No, just which one is thermodynamic or kinetic? Take your pick.
Oh. Kinetic, blue is kinetic because of our
So we would need to evaluate the transition state for the kinetic, because the transition state is what dictates the speed of a reaction. So I would need to look at a transition state. Do I have a transition state drawn yet?
No.
So we can't label the kinetic out of the gate. What could we label? The transition state is all, or the kinetic is all about speed. What determines how fast a reaction goes? The activation energy. If there's no activation energy drawn on this yet, I can't make that interpretation. Okay? What is thermodynamic dependent on? The lowest energy product. In this step, do I have a low energy product already drawn? Yeah, it's literally the one that's the lowest energy in that step. Intermediate 1, which would be our thermodynamic product.
So,
Whoa. Ah.
so it's fair to say maybe because it's more stable, obviously.
Because it is more stable, it is the thermodynamic product. Okay, so stability drives thermodynamics. Okay, what drives kinetics is speed, how fast it can happen. Okay,
That's the thermodynamic intermediate, not product.
true. It is our thermodynamic.
Words for me.
Yep, it is. And what we'll find as we continue to move through is that that product continues to stay as the thermodynamic product. Okay, or ends at the thermodynamic
Yeah,
product.
but as far, because that's an intermediate, you're not evaluating the product yet.
Fair. It's a thermodynamic intermediate. I'll accept that. Okay. And not just accept that. That's true. Okay. So let's bring in the transition state on this. Okay. We want to establish the transition states between these. My nucleophile has to come in and react with either of those. Is the nucleophile inclined to react with the alkene? Why not? How do alkenes react? Alkenes react as nucleophiles. What is the nucleophile going to do when it sees another nucleophile? Not react. Okay? Because I'm putting electrons near electrons, what happens to the transition state for the blue path? It should be very high because I'm putting too many electrons near more electrons. So I would expect my transition state to be somewhere up here.
That's only if you put another nucleophile.
If I take a nucleophile and I react it with the alkene, how do alkenes react? Like nucleophiles. That is by definition a nucleophile with a nucleophile. That's going to be a high energy transition state. Okay? What happens with the red path?
It's not as high.
The nucleophile is now attacking an electrophile. What happens to the transition state there?
Lower.
That's now going to drop. I'm putting negative to positive. That actually makes physical sense. Which is the kinetic product? The red one. The red one's our kinetic product because it has the lower transition state. Okay? So, or sorry, kinetic intermediate. What happens as we continue the reaction on? Okay, well, in the next step, I just add a hydrogen to the structure in both cases. Which of those is a more stable structure? The blue one. Okay, why?
It's more substituted.
It's still a more substituted pi bond, which means the blue one is still more stable, which means it is still lower in energy. Do I care about the activation energy in the second step? Why not?
So you're just adding a hydrogen to the charge,
I don't fully accept that.
because it's the same step.
It's a harder question. This goes all the way back to 152. Do I care about the activation energy in the second step? No, why not?
It's lower than the first one.
The activation barrier in the second step is lower than the activation energies in the first steps, which means that step is fast. The first step is slow step. When I look at kinetics in 152, my mechanism is always dependent on the rate limiting or the slow step. It's not the first step always, but it's always the slow step. The slow step was our first one. So I don't care about the activation energies in the next sequence. Okay? And those are going to be all out of sync because we have different energy intermediates.
Is it because it determines the rate of the reaction?
It does. It is because it determines the rate of the reaction. That's why we care about the slow step. Okay? Notice again the products that we're looking at. We said the top one was 1, 2, and the bottom one was 1, 4. Why do we see 1, 2 in the top one, in the red one? What did we add? We added the nucleophile and a hydrogen. If we went through and numbered, those things were added at the 1 and the 2 position. Everything's copacetic. That makes sense. What about in the blue one? What did we add? Nucleophile and the hydrogen. Interesting, By adding the same reagents, I get the same things added. Wow. Okay, amazing. Okay, but where did those new species now get added? The 1, 2, 3, and 4 positions. We have a 1,4 addition. Okay? Again, if we were put in the situation where we were given just a strong nucleophile, you would be expected to predict the 1,4 addition. Okay? And if you go through and look at answers, the product that you get for the 1,4 addition looks like this. What did you add?
Oh, looks like 1, 2.
We added the nucleophile and we added a hydrogen. Where? To the alkene. Does it make sense we're adding things to the alkene? What is the very first step doing? Adding things to the alkene. That actually kind of makes sense. That's the functional group that's reacting. It should do that. But why do I not, or why do I call this a 1,4 addition now? Because the intermediate does do a 1,4 addition. Once I form the enol structure, or the enolate structure, goes through, puts our negative charge back on that, so I'm redrawing that first resonance structure. Do I want a negative carbon? No, so what does it do? It picks up a hydrogen. Where does it pick up the hydrogen from? Anywhere in solution. Okay? If it's under acidic conditions, how should I make my hydrogen look? H+. It's now under basic conditions. H+ is now wrong. Because, right, under basic conditions, do I have H+? No. So where do I get the hydrogen from? Okay. I have to have an H, but it can't be H+. So one suggestion was H2O. Well, sorry, not that. H2O. Okay? Or methanol. Okay? Ultimately, there's tons of different places you could get that H from, which is why I would write it as HB. Okay? Where B is now just a base. Okay? Or I could even show it as HA. It's a generic thing. If it's under basic conditions, should HB be positively charged? No, because under basic conditions, what's my overwhelming charge? Negative. I can't have a positive base. Okay? Kind of, sort of. Lots of little intricate pieces that stack on top of each other, and we have to be careful when we go through and approach them. Okay? Yes?
Is 1,4 always going to be more stable than 1,2?
Always is a hard word to run.
Almost always?
Yes. Right. Because of the substitution pattern on that alkene. Could we theoretically generate a structure that would mess with that system? Yes, we could. We won't, but we could.
Okay.
Okay. Mostly okay with what's up there? Because I want to delete everything and draw your attention again to just one little section. Okay, so we're erasing everything. I want to draw your attention to that last step in the 1,4 addition. And that last step, what did I do? So number one, there's two arrows here, right? Where's the last step? Arrow 1 or arrow 2? Arrow 2. Why is arrow 2 the last step? Because arrow 1 is resonance. It's not a step. There's only one step shown here. Okay? In that one step, what kind of a reaction am I doing? I'm doing an acid-base step. Okay? So really what I'm adding is H+. Where should the H+ go? To the negative atom. So oxygen. Why would you say oxygen? Because the oxygen's negative and it's right next to it. God, Mike, they're right next to each other. And not only that, look at what we showed. I showed hydrogen attached to that oxygen. Was that a good maneuver? To predict reactivity, which resonance structure do you use? The worst. Which of those two structures is the worst resonance? Okay. Why am I showing it with the oxygen? I'm trying to get you to the idea of the 1,4 so that you recognize why we're calling it a 1,4. Everything about the chemistry puts it on that carbon, not on the oxygen. Kind of makes sense? Okay. So again, in this step, the way I've got it drawn was I placed the hydrogen on the oxygen. Did I do a good job placing the hydrogen on the oxygen? To decide where the hydrogen goes, okay, our acid needs to react with what? Something negative. I have two negatives. Which negative should I use? Okay. Why should I be using the left one and not the right one? Reactivity comes from the worst resonance structure, not from the best. The one on the right is the best resonance structure because the negative charge is on the oxygen versus on the carbon. Okay? So we're using these structures for different reasons to get at different pieces of information. We have to recognize how they're coded to be able to predict and follow these things through. Okay? In a mechanism, when should you draw resonance? Not whenever you can. Okay? For instance, we don't officially have a mechanism here. Could you draw resonance for that starting structure? Yeah. Did I draw resonance for it? No. In fact, drawing resonance for it is wrong. In a mechanism, you should not be showing resonance for that starting structure. When should you show resonance in a mechanism? When it explains why a step happens. A step would produce charge, so we're using resonance to explain why charge is stabilized, why that charge is allowed to form. Okay? Can we use resonance to help us predict where things would react? Absolutely. If I drew resonance for that starting structure, I would see that there were two sites of positive character. Those two sites of positive character now allow me to know that the nucleophile could attack two different places. Drawing that resonance structure now is invalid in a mechanism because that structure doesn't exist. Why does this structure not exist? Look at it. Yeah, it's a good answer. Look at it. Why is that a bad thing to draw right now? It doesn't exist because of all the charge within it. Why, when I draw it an intermediate, do I now start to look at resonance? Well, I've got charge in it. Am I allowed to do charge? I've even heard something that makes me want to vomit with the purple resonance. It seems a bit over the top, I thought. Okay. I'm allowed to, but my first step shows charge. Shouldn't I be equally vomiting here? Okay. There's less charge. How do I know there's less charge? Okay. Numbers of charges, and what can I do with that charge? I can do resonance to show that that charge is allowed to form. Resonance is shown only when it is something that shows why you could do a step. It is not used to explain the start of a step, officially. Okay? Yippee-ki-yay. Okay? So, as far as our nucleophilic additions and being reversible, okay, we've seen reversibility when we go through and look at pKa's. You can make pKa arguments within this. It's not easy to go through and do. This is an old slide, but we could theoretically run something with looking at pKa's. Ultimately, it's going to be very hard to look at pKa's because what did I generate? A base. So looking at a pKa for a base is not really a good idea because it's not an acid. It's a base. So what would I have to look at if I wanted to use pKs to evaluate reactions, or these types of reactions? I would have to look at its pKb. That gets a lot harder to deal with and usually isn't worth the trouble, but we could theoretically do something along those lines. Okay? We can look at pKa's and make these comparisons to predict something about the strength of the nucleophile and how quickly it would react. Okay? It's a bit out there. We could do it. I don't think it's worth the time, personally. Thank you for the second. If you would like to talk to me more about it, we can. Ultimately, what you need to know is this table in your textbook that talks about reversibility. Because kinetic and thermodynamic is all about reversibility. Okay? Which product do I get at the end of this reaction? The blue one or the red one? The red one or the blue one. Good answer, because it was a horrible question. Let's try it again. Which product do I get first? I get the blue one. Okay? So I get the kinetic product first. But what if I use a weaker nucleophile? Okay? I'll still get the blue one first. But because it's a weaker nucleophile, what happens to the activation barriers all the way through that? They get smaller, which means what happens? It's reversible. The instant it's reversible, now what happens is some portion of it forms the thermodynamic. Can I reverse the thermodynamic? No. So if I use just a strong nucleophile, I still form the kinetic first, because the kinetic always forms first. But a strong nucleophile is now reversible, which gives me the opportunity to form the thermodynamic product. The thermodynamic product is now non-reversible, and I get only the thermodynamic product. Okay, so that difference now comes in referencing our nucleophiles. Okay? If I have a nucleophile that adds irreversibly, okay, first I form the kinetic, but it's now an irreversible addition. Can I reverse the reaction?
With the kinetic, with part of the kinetic, though, Kane.
If I use an irreversible nucleophile, can I reverse the kinetic product?
Change my answer to no.
No. Okay, I can't. By definition, I can't because it's an irreversible nucleophile. So I only get the kinetic product. The kinetic product was which product? Keep going. Fastest is true. The direct, keep going. 1, 2. All of those are valid descriptions. I would argue 1, 2 is probably the easiest to memorize because that's telling you directly where to put those things. Okay? What if I use a nucleophile that is now reversible? I'm still going to form the kinetic, but now it could reverse back, giving me the opportunity to make the thermodynamic. The thermodynamic is now irreversible. Okay? So note, we're using reversible and irreversible at different times in our system. In one case, we're referencing the nucleophile. In another time, we're referencing the difference between kinetic and thermodynamic. Okay? So when we talk about kinetic and thermodynamic, you have to be specific to what you are referencing. If I'm talking about a reaction that is reversible, you should be talking about the kinetic.
But then thermo.
True, sorry. If I'm talking about a reaction that's reversible, it would be kinetic. Okay? What product would I get if I had a reversible reaction? I get the kinetic first, the kinetic reverses, and I only get the thermo. And it's only get the thermo. Why would I only get the thermo? What is the time span it takes for a reaction to run?
It depends on what.
Most reactions are in sub-milliseconds. You're forming these products nearly instantly and they immediately move back. When we have longer time frames for reactions, those longer time frames are because they are equilibrium reactions, and we're trying to get it enough time so that it can get to equilibrium so that we can get a high enough product yield.
So you're saying a reversible reaction, got the kinetic first, when it reverses, I only get whatever happens to
You
the
will
arrows.
only end at the end with a thermodynamic.
What happened to the arrows where the product comes back?
It's-
Some goes to kinetic, some
If
goes
it's
to
a
thermo.
reversible reaction, we get the kinetic, because the kinetic is a reversible reaction. So if we're only referencing the reaction, kinetic is reversible, thermodynamic is irreversible. Okay? So if I get a reversible reaction that is kinetic, the product that I get, or sorry, a reversible reaction, the product that I get at the end is not the kinetic product. Because I form the kinetic, and then what does it do? It reverses, giving me opportunity to make thermodynamic, which never reverses. Because it never reverses what happens to the equilibrium between reactants and kinetic.
Never happens.
It shifts to constantly form reactants. Because the reactants keep disappearing to form thermodynamic.
Okay. No.
Okay. Make sure that you're using kinetic or reversible and irreversible correctly, is ultimately what it comes down to. If we're going to reference reversible and irreversible, we don't want to reference the reactions because kinetic and thermodynamic can be dangerous. Because depending on the conditions that that said reaction is running under, it could be kinetic, it could be thermodynamic. So when do we use reversible and irreversible?
Depending on the condition.
With the conditions. So I will reference nucleophiles as irreversible nucleophiles. Okay? As an irreversible nucleophile, what product do I get? Kinetic. Is that kinetic product reversible?
It's irreversible.
It was irreversible. Why was it irreversible?
Because the nucleophile.
Because of the nucleophile. If I run a reaction under new conditions where my nucleophile is now a reversible nucleophile, which product do I get first? Kinetic, but the kinetic product is now reversible, and the product I get at the end is thermodynamic. And the thermodynamic product is now irreversible.
So do we just want to form a thermodynamic product, so just another?
I add Grignard. Do I form the thermodynamic product? No, you have to base it off of the conditions. You can't make a blanket statement, I always want to form thermodynamic. It doesn't work. You have to look at the nucleophile. So when we're using reversible and irreversible, the only label that doesn't change is on the nucleophile. If you label kinetic and thermodynamic as reversible and irreversible, that will change depending on the conditions of the reaction. So when we use the words reversible and irreversible, we want to keep them only in reference to the nucleophiles. Okay? Not to kinetic and thermodynamic. Okay? Is there another thing other than nucleophiles that we could tie reversible and irreversible to? Temperature is an option. Okay? Because if we have high temperature, what happens? What happens to the reversibility with high temperatures? It increases. And all of my reactions become reversible. Okay? Which one becomes less reversible? Thermodynamic, meaning I get the thermodynamic product at high temperatures. So temperatures are conditions that we could label as reversible and irreversible. High temperatures would be a reversible process. What's the other condition that we could label? Low temperature I would group in that same category. Not quite. Just the base, strength of the base. When we're forming enolates, okay, on asymmetric enolates. Do we have a stupid strong base? Well, stupid strong bases are irreversible, which means the enolate that I form is the kinetic enolate. Not reversible or irreversible. I remove that from the system. I have to call it the kinetic enolate. Okay. What if I used a weak base or weaker base? Then it is a reversible acid-base reaction. Which product do I get? I get the thermodynamic. Okay. Because the kinetic reversed. Okay, so you have to be careful on labeling reversible and irreversible on kinetic and thermodynamic because the conditions will change those labels. Okay? And whether you're happy or not, we could go through and take a look at these. So if we tried to evaluate out For that first reaction, what would you expect? Mostly the right product. Why? The Grignard is stupid strong, which means it's an irreversible product, so it's going to form the kinetic, and now that's irreversible. I get the direct addition, the 1, 2. How about the next one? What is the nucleophile in the next one? O minus. Is that stupidly strong? No. So where does that just strong nucleophile attack? Okay. It ends up attacking the alkene. Okay, so that we can form which product? The one on the left, which happens to be the thermodynamic product, which looks like a 1, 2. Again, we aren't even showing that intermediate with the enol. We're going directly to the final product. Okay. Last one. Oh, we just talked about lithium, right? Lithium was that weaker one, right? No.
But it should be the left product.
What with the copper, the lithium one, when I followed it with copper, was then a reversible nucleophile. No copper makes this irreversible, and I get the kinetic 1, 2.
So it decreases it that much that it can do the.
Yes.
If you do have the copper, then you would get.
If we had the copper one on there, we'd get the right one for the bottom one. Right? This is our kinetic 1, 2.
Then they're all non-reversible, right?
Technically. What's all non-reversible?
Well, I know that kinetic should be reversible, but.
Well, this is a kinetic. If you just said all the kinetic are non-reversible. Okay, so the top one is the kinetic non-reversible.
According to what we just learned.
According to the structure that we circled as the final answer, what did I obtain? The kinetic product or the thermodynamic? The kinetic, which by definition means the kinetic in that circumstance was irreversible. Why was it irreversible? Because of the irreversible nucleophile used. Right? And the second one, was it the kinetic product? No. So what does that mean the kinetic product was? Reversible. Right? It had to be reversible because if it didn't reverse, what would our product be? Kinetic. Okay? So it was a reversible product. Because a reversible nucleophile. So the labeling of reversible and irreversible is not on the reaction, it's on the reagents. It's on your conditions. That's where you have to keep it. Okay? We can only label our reactions when looking at a specific circumstance, okay, or a specific energy diagram. Okay? Whoa! So our Gilman reagents, okay, we're generating it. So carbon with copper, sometimes you'll hear these referred to as organocuprates. Cup for copper. Right? So if you see an organocuprate, cup, C-U-P-P, for cuprate you do. Okay. You're looking for copper. And it does make sense for the symbol used because it goes back to the Greek prefixes. Okay. Cuprous and cupric. Okay. Copper is the English language getting a hold of the name. Okay. So your organocuprates, strong nucleophiles, but not stupidly strong, which means which of these two is the correct product? Okay. The second one. We get the 1,4 addition. The 1,4 addition happens to be which product? You could say right, but I've now eliminated that answer. You can't say left because it's the one on the right. The 1,4 is our Thermo product, okay, which also referenced as our conjugate addition. Okay? What is the difference between our Grignard and Gilman? So we go strength and nucleophile, acceptable. What's the other difference?
The types of products.
We see a difference in the type of products. Why do we see different types in the products?
Attacking the electrophile versus the nucleophile.
Okay, so that's the strength of the nucleophile again. What's our difference between our Grignard and Gilman? You're all right. I want more. With Gilman, we look at copper, and with Grignard, we look at magnesium. There's our big difference. So that's why we're seeing the difference in reactivity there. That subtle difference in electronegativity is enough that we switch from reversible to irreversible reactions.
In this, can you it doesn't matter if you use ammonium chloride?
No. Typically with the copper you see ammonium chloride, but all you need is something remotely acidic. Ammonium chloride is remotely acidic because what we're looking at there is NH4 plus and Cl minus. Cl minus is a spectator, so we can erase that. We're looking at NH4 plus. Does nitrogen want to be positively charged? No, so what does it do? Steals electrons from the hydrogen, and we now have H plus. So ammonium chloride is just an acid source. It just happens to be a weakish acid source. Okay. HCN, it's another type of reaction that we can do for our nucleophilic additions. HCN known as, say that again? Cyanic acid. So cyanide, okay, is the root there. CN, when we put a hydrogen in front, it's now an acid. As an acid, it's probably the most reactive thing there, so what's the first thing that happens? We protonate the oxygen. Oh, wow, that arrow got swervy. Okay, we protonate the oxygen. What happens? We would get a positive oxygen. Does oxygen want to be positive? What does it do? Takes electrons from the pi bond, freeing up the carbon to be attacked by the cyanide. Right? The cyanide, in a sequence of a whole bunch of other steps, can be converted to an acid. Notice parentheses. Why are they showing parentheses?
Because that's the overall product.
There's a whole bunch of stuff that happens there.
There is a whole bunch of stuff that happens there. There's another reason.
Same thing over.
You aren't responsible for it yet. That chemistry that's happening when we do the hydrolysis is nucleophilic addition followed by elimination. All we're looking at so far is nucleophilic addition. So you just aren't quite responsible for that next sequence within it. Okay? To do that, you have to have water present, because if we look at our structure, that's an OH. What do we have there? Triple pi bond is fair, or sorry, a triple bond is fair. It's not an alkyne because there's a nitrogen, you'd call it a cyano, hence cyanide. A polar pi bond. What could react with a polar pi bond? A nucleophile. This is where water comes, whoops. Water as a nucleophile in this reaction could come in and attack, okay, and then attack, and then another water can come in and attack again. So 3 attacks of water into that, what happened to the nitrogen? It left. Okay? So we end up doing nucleophilic addition, nucleophilic addition, nucleophilic addition, followed by elimination of the nitrogen. Okay? So we will see that. The pattern of that chemistry is the same pattern for the nucleophilic addition. We just add an extra step at the end of it. In theory, it's not that much more difficult. That'll be our 3rd unit, and we'll see things to make it more difficult then. Okay? I don't want to look at synthesis right now. Here in glory is chapter 18. Okay? And some of our 17. So the left-hand side, what's attacking our carbonyl? Big letters at the top of the page. Carbon. Grignard, cyanohydrin, Wittig, all of those are carbon nucleophiles. Okay? Right through the middle section, what's attacking our carbonyl? Oxygen at the top, nitrogen. Okay? Carbon tends to be a stupid strong nucleophile. Our oxygen and our nitrogen tend not to be. Okay? Because of that, their chemistry slightly changes some of the reactivity. That's why you went through and watched that video that I probably need to go through and adjust so the timing isn't horrible here because we only got 2 minutes left. The oxygen and nitrogen nucleophiles are by definition weak nucleophiles. And because they are weak nucleophiles, we now have reversible reactions. Because we have a reversible reaction, we now have
The kinetic product.
reversible reactions
Equilibrium.
gets us our equilibrium. Right? So this little fun thing is just word association gain from equilibrium because everybody hated 152. Ultimately, what we are doing in this section is you just have to deal with equilibrium. Everything that's getting addressed in this chapter is all about equilibrium, and it makes dealing with that chemistry a lot more challenging. Okay? So don't worry about it. Okay? But big rules. Do not break your Lewis structure or curved arrow rules. Okay? So to give you a quick example, and the only reason I've got this example is because someone asked about it, so I won't name names, but you know who you are. What does it appear happened here? Shut up.
Okay, it looks like.
Okay? Resonance, we can accept that. Okay? And this is, and what I'm carefully fishing for the wrong answer. Okay? Most people look at this and say that the double bond moved places. No, not really. Okay? Because when we reference the double bond moved places, what you're telling me is that the purple pi bond did this. It moved places. No, it didn't. Where did the purple pi bond go? To a hydrogen. What's the difference between these two structures? When we fix the carbon, this had 2 hydrogens. That one has 3. Okay? So we have to be a little bit more careful about how we approach looking at these differences. That's why you have to be very careful with your Lewis structures, very careful to not break octet rules or curved arrow rules. Do not exceed octets. Do not lose octets. Move electrons always from a source to a lac. Okay? That arrow to cause the pi bond to move up there, you're moving the pi bond, a source of electrons. Good move, but where are you moving them towards? Something that has 8 electrons. Is that something that lacks electrons? No. Okay? So that doesn't work. What is underneath there? That doesn't work. What's happening is our electrons move down from the nitrogen to make the new pi bond. The pi bond breaks and reacts with H+. I apologize for talking too long, but I did want to at least address those big things. This is a hard section to deal with because everything is equilibrium.